Hi there, I'm Sarah Buett. I'm from Victoria University of Wellington, and this is my paper on the disparity between reality and theoretical models, specifically when predicting moisture and mold growth in homes. So the Housing Conditions Survey undertaken by Brands was a survey which looked at a variety of randomly selected houses throughout New Zealand and surveyed things such as basic amenities as well as the presence of heaters and other space conditioning systems. One of the other things that it did assess was whether there was any mold present in the homes, and it found that of the assessed properties, 46% of owner-occupied homes and 54% of rental homes experienced mold. Whilst the survey did not look at all New Zealand houses, it does suggest that there is a significant mold problem for many New Zealand houses. There are many clauses within the New Zealand Building Code, and specifically Clause E3 focuses on the presence of internal moisture and mitigating any moisture-related problems within buildings. It's also important to note that the New Zealand Building Code is a performance-based code, which means it states how a building must perform as opposed to providing a prescriptive compliance method. Due to this, compliance is often achieved through implementing common wall constructions like the one shown in Figure 1 on the left here. Another method that can be used to show compliance is through the use of moisture analysis tools and standards such as ASHRAE Standard 160, which is the criteria for moisture control design analysis in buildings. The key thing that this standard does is to create a scenario where the internal conditions are not known and implement several assumptions into how people use their homes and what this in turn means for what the internal conditions such as temperature and relative humidity are likely to be, which are two factors critical for mold growth. The aim of this research was to understand whether the assumptions are suitable for New Zealand homes and whether they are able to be used to successfully create internal conditions that would actually be experienced in New Zealand homes. So this is a flowchart showing how this research was undertaken. The PHS is the Pilot Housing Survey, which was another survey undertaken by Brands, which looked into placing sensors into 80 homes throughout New Zealand. Each of these homes had 6 sensors placed, one in the living area, one in the roof space, one external sensor, and then the other 3 were placed in bedrooms if there were 3 bedrooms available. So this research takes the data from one of these houses, utilizes the information from each of those sensors. It excludes the roof space and the living area sensor, as roof spaces are out of the scope of ASHRAE Standard 160, and the living area sensor was found to not be calibrated properly. And it takes the information, which is the temperature and relative humidity of each of those sensors. This information was recorded approximately every 15 minutes for around a year. And then on the other side, we're going to take ASHRAE Standard 160 and utilize the data gathered from the external sensor to determine indoor design temperature and indoor design humidity, which will then specify a set of internal conditions. And we're going to compare the specified and the measured internal conditions in order to understand any discrepancies that may arise. So this table here shows the formula that ASHRAE Standard 160 implements to suggest the indoor design temperature. ASHRAE Standard 160 assumes that the indoor design temperature is directly related to the outdoor temperature and specifies it as one of 3 values, all dependent on the 24-hour running average of the outdoor temperature. This is particularly important for New Zealand, as the New Zealand Building Code has no minimum indoor temperature requirement, except for in old people's homes and early childhood centres where a minimum of 20 degrees is required. The equations shown in the table demonstrate that the indoor design temperature assumes that there is a minimum heating set point within the space of 21.1 degrees, and this is based on the idea that the average outdoor temperature falls below 18.3. And if this were to happen, then the indoor temperature would fall below a comfortable temperature, thus requiring heating. This results in an assumption that all the spaces that are assessed under ASHRAE Standard 160 have some form of space heating to ensure this minimum temperature would be achieved regardless of the outdoor temperature. So when looking at the indoor design humidity, ASHRAE Standard 160 allows for this to be determined through one of three methods: the simplified, the intermediate, and the full parametric calculation. This paper will just look at the simplified method. So the table shown here explains the formulas which should be applied, and similarly to the indoor design temperature, the indoor design humidity assumes that the humidity relates to the outdoor temperature. The critical assumptions here are that it assumes that the humidity will never drop below 40% or exceed 70%, and there is also no consideration of any presence of dehumidifying systems. So by applying the formulas that we saw beforehand, the following graphs are produced. The main part of the graph that should be focused on is the green line, which is what ASHRAE 160 specifies as the indoor design temperature. So applying these calculations to the collected data from the pilot housing survey, the indoor minimum of 21.1 degrees is applied 78% of the time, yet the graph shows this is higher than the measured temperature for approximately 6 months. It's the straight line from March to the end of the year. We can see that from approximately the 2nd of March to the 10th of September, the average measured outdoor temperature was below 18.3 degrees for 98% of the time, which resulted in the indoor design temperature being on average 2.7 degrees higher than the measured temperature. During the winter months of June to August, this deviation from the predicted indoor design temperature increased by up to 6.2 degrees. In contrast to this, when the outdoor temperature was below 18.3 and 21.1 degrees, the indoor temperature calculation is more directly related to the outdoor temperature. And this is the first 2 months of the year that you can see there on the left. In these instances, the ASHRAE standard formula simply adds 2.8 degrees to the 24-hour average outdoor temperature. The graph shows that this relationship is much more applicable and more closely follows the measured indoor temperature. From the 20th of February to the 1st of March, the average outdoor temperature is between 18.3 and 21.1, and therefore due to this adds 2.8 degrees, and it results in an average difference between the measured data and the indoor design temperature of just 0.4 degrees with a maximum deviation of 2.9 degrees. So again, applying the formula shown before to the measured data, the following graph is produced for the indoor design humidity and shows the differences between the conditions specified by ASHRAE Standard 160 and the measured data. So just as the indoor design temperature specified an absolute minimum of 21.1 degrees, which results in a variation from the actual measurements, the indoor design humidity is specified to have an absolute maximum of 70%. This is achieved when the daily average outdoor temperature exceeds 20 degrees, and it assumes that warmer temperatures have higher saturation vapor pressures. However, relative humidity is not solely determined by the saturation vapor pressure, but also by the partial vapor pressure. This means that just because a temperature of over 20 degrees is experienced, the partial vapor pressure will not necessarily result in a relative humidity of 70%. This is demonstrated in the periods between the 12th of March and the 1st of April, where the indoor design humidity specifies 70% humidity, but on average over this time period, the relative humidity was 63%. The indoor design humidity gave an indoor relative humidity exceeding the actual, which may result in false positives for mould growth. Discrepancies regarding this 70% relative humidity maximum also arise when looking at situations where the measured data exceeds 70%. Relative humidity of 70% was exceeded approximately 10% of the time for each of the bedroom sensors. but on only one day, specifically the 23rd of February, did the daily average outdoor temperature simultaneously exceed 20 degrees. So this demonstrates several things. Firstly, relative humidity exceeding 70% is common within this house, and the indoor design relative humidity does not consider the implications of this. And secondly, a relative humidity exceeding 70% is able to be achieved within the temperature below 20 degrees. In situations where the relative humidity exceeds 70%, the temperature averaged at 18.5 and even went as low as 14.9. In these circumstances, the indoor design humidity is specified a relative humidity that is lower than what is being experienced within the space and therefore may also produce inaccurate results. Another important thing to consider is that existing mold prediction models place an emphasis on the impact of unfavorable mold growth conditions. An unfavorable condition would be one where either the moisture content or the air temperature are such that the mold is unable to grow or could even reduce. So when there is a large range in relative humidity, there are points at which the humidity could be potentially unfavorable and therefore where unfavorable conditions could occur. This is potentially the case when looking at the measured data, where the recorded relative humidity range of the bedrooms could be as much as 28%. A fluctuation this large in the humidity suggests that there would be time periods where the mold growth conditions would be unfavorable. However, in contrast to this, the indoor design humidity modeled only fluctuates by 11% throughout this time period, suggesting that ASHRAE 160 may be flattening out extreme fluctuations in humidity, which may negatively impact the assumptions of unfavorable mold growth conditions that may be experienced. So to conclude, when looking at indoor design temperature, the graphs showed that the fixed minimum indoor temperature of 21.1 degrees when the outdoor conditions drop below 18.3 is not applicable for many of the heating regimes in New Zealand houses, and rather a more direct relationship of adding 2.8 degrees to the outdoor temperature was favourable and better matched the measured indoor conditions. In several instances, the indoor design temperature specified a room that was on average 2.7 degrees warmer than it actually was, and this in turn may result in false positives in mold predictions. When looking at indoor design humidity, the maximum of 70% relative humidity was frequently exceeded, indicating that this standard may not be suitable for unconditioned houses. And the analysis also showed that a relative humidity of 70% is also able to be achieved frequently when temperatures are below the 20 degrees that is indicated in ASHRAE Standard 160. Furthermore, the differences in the fluctuation of the relative humidity further indicated that the ASHRAE Standard 160 could be flattening out extreme fluctuations in relative humidities, which may negatively impact the assumptions of the frequency of unfavorable mold growth conditions. So to build on what has been previously investigated, this research will continue to look at the intermediate method for indoor design humidity, which aims to understand how the increase in inputs can alter internal conditions that are predicted. So things such as moisture generation rates, ventilation rates, these kind of things. The same analysis shall be run with the other 79 houses from the pilot housing survey, and this will be in order to understand whether there are trends in the assumptions that are made and whether conclusions that were drawn in this research are applicable to a number of other houses throughout New Zealand. And lastly, this investigation into whether the internal conditions that are predicted by ASHRAE Standard 160 would impact the final outcome of mold predictions, and this will be through utilising a computer analysis tool such as Woofy Pro and inputting the likely indoor conditions